Imagine a world where the tools you use to build the future are the ones that build themselves. For a long time, this sounded like science fiction. Then came AlphaEvolve. This was a coding agent designed for scientific and algorithmic discovery. It was a massive step forward because it could autonomously discover new matrix multiplication methods and optimize hardware without direct human intervention. For a brief moment, it felt like we had cracked the code on artificial research. The excitement was palpable across the engineering community. We thought we had found the ultimate engine for innovation. But here is the thing that often gets overlooked in the rush to celebrate new technology. AlphaEvolve is already obsolete. It is not just outdated, it is fundamentally limited by the very architecture that made it successful. To understand why, we have to look at how it worked and where it hit a wall. AlphaEvolve relied heavily on the internal knowledge of a large language model. This means it used its own training data and context to generate code, test it, and iterate. It was like a brilliant student who only had access to their own notes. They could do well on familiar problems, but when the exam changed, they struggled to adapt. As the complexity of scientific domains increased, this reliance on internal knowledge became a bottleneck. The agent could optimize existing methods, but it could not discover truly novel concepts in chemistry, mathematics, or biology. It plateaued. The improvements became shallow. It was a static architecture trying to solve dynamic problems. The system was trapped in a loop where it could only refine what it already knew. It could not reach beyond the boundaries of its own training data to find the next breakthrough. This limitation was not a bug. It was a design constraint that became a liability as the field advanced. This is where the narrative shifts from the past to the present. We are now seeing the rise of frameworks like EvoX and DeepEvolve. These systems represent a fundamental shift in how we approach automated discovery. They do not just evolve code, they evolve the process of evolution itself. This is known as meta-evolution. Instead of a fixed set of rules for how to search for solutions, these agents dynamically restructure their own search spaces. They can change the rules of the game while they are playing it. This allows them to sustain gains across multiple disciplines where AlphaEvolve would have stalled. Consider the difference in terms of a search strategy. AlphaEvolve was like a miner digging in one spot, hoping to find more gold by digging deeper. EvoX is like a surveyor who can analyze the geological data, see where the gold might be elsewhere, and move the operation to a new location. This ability to augment evolutionary search with deep external research is the key. These newer agents can retrieve knowledge from outside their immediate context. They can read papers, access databases, and integrate findings from other scientific domains. This breaks the isolation that trapped the earlier models. Now, consider the specific angle of the next transformer. When people talk about the next transformer architecture, they usually think of a specific neural network layer or a new attention mechanism. But in the context of automated discovery, the next transformer is actually the system that discovers it. AlphaEvolve optimized the existing architecture. It made the machine learning models run faster or use less memory, but the new meta-evolutionary frameworks are capable of discovering the underlying structures that define the next transformer. They automate the discovery of the discovery process. This is a nonlinear acceleration in AI capabilities. The gap between what is possible with code evolution alone and what is possible with research augmentation is widening rapidly. This brings us to the engineering trade-offs for scaling data systems. If you are building a system that relies on pure code evolution, you are betting on a static approach. As your data scales, the validation bottleneck becomes the primary constraint. You generate more code, but you spend more time verifying it. The hybrid models that combine code execution with external knowledge retrieval solve this by reducing the search space. They do not guess blindly. They use retrieved knowledge to guide the generation. This makes scaling feasible. It allows organizations to handle larger data sets and more complex problems without the engineering team becoming overwhelmed by the validation workload. The transition from AlphaEvolve to these newer agents marks a shift from human-guided coding agents to autonomous entities. They generate novel algorithms beyond human expertise. This suggests a future where the primary bottleneck for discovery shifts from algorithm design to validation and integration. We are moving from a time where humans had to write the instructions for the machine to a time where the machine writes the instructions for itself. The role of the human expert changes from a creator to a validator. They are no longer the ones designing the solution. They are the ones ensuring the solution is safe, accurate, and integrated into the broader system. The rapid obsolescence of AlphaEvolve highlights a non-linear acceleration in AI capabilities. Meta-learning and automated strategy finding outpace traditional evolutionary approaches. This makes static agent designs unsustainable for cutting-edge research. If you are relying on a system like AlphaEvolve for discovery right now, you are already behind. The field has moved toward more robust, research-augmented methodologies. The consensus is clear. While AlphaEvolve was a pioneering step, the trajectory is now toward systems that can restructure their own search spaces dynamically. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.